All right, here it is, the last lesson for the unit. So we're going to try to tie together a lot of the pieces that we've been working on throughout this unit in this. There's really no new skills that you need to know for this lesson, but we are going to start taking these little pieces and then put them together into some bigger problems. So these will take a little bit longer to do, but like I said, there really shouldn't be anything new that we're covering here. So first off, you need to keep in mind that chemists rarely do one-step calculations. All of the homework, I was trying to give you things that help you practice this specific skill or this specific skill or Hess's law, like those little pieces individually. But rarely does a chemist only do one piece. He's trying to solve a bigger problem. So you're going to have to take all the pieces that you've kind of learned and put them together. So very first, let's just go through the formulas and some of the stuff that we've covered. So remember that the first thing you should always be asking yourself on any of these problems, is it a temperature change or a chemical change? If it's a temperature change, then your formula is Q equals MC delta T. If it's a chemical change, did I say chemical? That's temperature. I hope I said that right. If it's a chemical change, then your formula is delta H is equal to N delta HM, or remember the other version of that is delta H is equal to mass over molar mass delta HM. Just whether you're looking for or are given moles, or whether you are given or are looking for the mass of the thing involved in the chemical change. And then we went through that you could combine those. Remember, like in calorimetry, we can say that heat lost is equal to heat gained. And then we can combine bits and pieces of the Q formula or the delta H formula to build this out into something like, let's say a mass over molar mass delta HM is equal to an MC delta T. So just combining the pieces together when you have both changes happening simultaneously. And then we've also done our Hess's law. So delta H is equal to sum of the N delta FHM of the products minus, that bracket, minus the sum of the N delta FHM of the reactants. So those are all the pieces that we might be using on the problem, and then we just have to decide based on the problem which one is appropriate for us to use and in what order to use them. So let me show you how this works. So if you look at example number 1, what quantity of energy can be obtained from the roasting of 50 kilograms of zinc sulfide ore? And then they give us this unbalanced equation. So we've got zinc sulfide plus oxygen is going to become zinc oxide plus sulfur dioxide. So to balance this, we're going to go 2, 3, 2, and 2. So just to save time, let me just throw that in. All right, so balanced equation, there we go. Now the question is saying what quantity of energy. So we're looking for not a molar enthalpy, but just total amount of energy, which is either a Q or a delta H, whether we're talking about a temperature or a chemical change. And since they gave me a chemical reaction, I know it's chemical change. So what I'm looking for here is delta H. And since they don't mention a temperature change, I'm only looking for delta H. Now, whether I use N or mass over molar mass, if we look at the question, it tells me I have 50 kilograms. So instead of N, I'm going to use mass over molar mass delta HM. And then we can start substituting in and we should be able to find it. But you're going to notice there's something missing. So let's see what we've got so far. We've got 50 kilograms. I'm going to change that to grams just because I know my molar mass is going to be in grams per mole. So I have 50,000 grams. And the molar mass of zinc sulfide is 97.48 grams per mole. Okay, so those grams are going to cancel. And then the next thing I need is a delta HM, but I don't have one. This question doesn't give one to me. Here's one trap that a lot of people fall into. don't go to your data booklet and use the delta FHM for zinc sulfide. The reason you can't do that is remember that those numbers in your data booklet, actually let me see if I still have it up here. The numbers on this page, remember if you read the top, are molar enthalpies of formation. These numbers you could have used if this was a formation reaction. But the problem we're working on isn't a formation, it's a roasting or a type of combustion. So I can't use formation numbers directly in that formula. But I can use them in Hess's law. So in order to find delta HM, I'm going to do Hess's law to find delta H and then convert it into delta HM. So I've got the sum and delta FHM of the products minus the sum of the N delta FHM of the reactants. And I try to squeak this over so I got some room here. We have product side 2 times zinc oxide, which is negative 350.5, plus 3 times, or sorry, not 3, looking at the wrong side. 2 times sulfur dioxide, negative 296.8. On the reactant side, I have 2 times the zinc sulfide, which is negative 206, and then plus 3 times 0. Okay. Now, if you do that all out in your calculator, you should get, I think it's negative 882.6 kilojoules. Now remember, that's a delta H value. Actually, let me slide that over so I got some more room here. So delta H is equal to negative 882.6 kilojoules, if I did that right. But over here in this problem, remember I need a delta HM, not a delta H. So I need to change this by taking that and dividing by, my balanced equation has 2 moles of the zinc sulfide. So then I get negative 441.3 kilojoules per mole. That's the delta HM. And now I can put that in my formula over here. Now remember over here though, we usually in this, let me back up. Remember that in Hess's law, this formula, we put in those negative values. When you do this formula, you don't. Because if you're solving for mass or for something else, those negatives will mess you up. But you may have to put it back in at the end. So here I'm just going to put 441.3 kilojoules per mole. And now that per mole is going to cancel with that per mole. And I'm going to be left with an answer in kilojoules, which I think is 226,354 kilojoules. Now that's a big ugly number. Remember in this unit we quite often change the metric units just to make it fit our significant digits, which in this case is 3. So I would make this 226 megajoules. And that solves the problem, except for remember that there was two things we always ask ourselves. Oh, I'm in the way of that. Is this temperature, chemical change, or both? This one was temperature, or sorry, chemical. And then the second problem you ask yourself at the end, is this exothermic or endothermic? And since this is exothermic, I have to put that negative value in, and that's my final answer. So it's a little bit long, it's a little bit of stuff, but it's nothing new. Hopefully that's not too stressing to you. But I'm going to cut this one off, and then I'm going to do another video on the second example, and then you guys will be on your own.